There's a thing that happens when you stop trying to fall asleep, when you've been lying there long enough that your thoughts go a bit loose, stop finishing themselves, and the room gets heavier somehow, even though nothing's changed. The blanket weighs what it weighed. The dark is the same dark, but something shifts. Your attention starts moving differently, slower, wider, and for a moment, just a moment, you stop being a person waiting for sleep and become something more like a field. Aware, but barely. Present, but not insisting on it. That's roughly the closest I can get to describing where this begins. Not with a bang, not with a dramatic rupture, with a cloud, and I know that sounds underwhelming, maybe even a little silly, given what the cloud eventually becomes. But I want to stay with it for a while before it becomes anything, because the cloud, for most of its existence, was not becoming. It was just there, enormous and directionless and cold in a way that has nothing to do with cold weather. Cold in the sense of almost no energy moving between particles. Cold in the sense of very little happening spread across a distance so large that our usual ways of measuring things start to feel faintly embarrassing. This was a molecular cloud. That's the actual term, a giant molecular cloud if we're being precise. A region of interstellar space dense enough with gas and dust to allow molecules to form and persist. Hydrogen, mostly, some helium, traces of things heavier but not much. The whole structure, and calling it a structure feels generous, could span hundreds of light years. Hundreds. A single light year is already past the limit of any intuition I trust. Hundreds of them, and the cloud just sat in them, occupying that space without urgency, without trajectory, without any apparent intent. And it had been doing this for a very long time before anything changed. I used to think, and I mention this only because I suspect I'm not alone in it, that the origin of the solar system was a kind of event, a moment, something you could point to on a timeline and say, here, this is where it starts, the explosion, or the collapse, or whatever violent thing you imagine when someone says formation. But that framing is wrong, and not just slightly wrong. It's wrong in a way that obscures something genuinely strange about what happened. The solar system didn't start. It accumulated. It condensed. It organized itself out of material that had been waiting more or less patiently for something to tip it over. The cloud was not in equilibrium exactly. Nothing at that scale holds perfectly still, but it was close enough to stable that it persisted for millions of years without collapsing. Two forces held each other roughly in check. Gravity, which pulled every particle toward every other particle, and the thermal pressure of the gas itself, which pushed outward, resisted compression, kept things spread. Not a standoff, really, more like a very slow conversation between forces that disagreed but hadn't yet reached a conclusion. And then something happened. What that something was, this is where I have to slow down, because the honest answer is that we don't know with certainty, and the almost certain answer is both more interesting and more strange than a simple something exploded nearby. The leading theory, the one with the most physical and chemical evidence behind it, is that a shockwave passed through the cloud. From a supernova, a massive star, somewhere in the neighborhood, that had burned through its fuel and collapsed and detonated, as massive stars do, with a force that sends ripples outward through space at tens of kilometers per second. That shockwave hit the cloud, and the cloud, which had been suspended in this long, quiet, almost geological non-event of a stability, was compressed, just slightly, in some places more than others, and in the places where it was compressed, gravity gained a small advantage, density increased, which increased the gravitational pull, which pulled in more material, which increased density further. Not fast. None of this was fast, but it was self-reinforcing, and self-reinforcing processes, given enough time, tend to reach conclusions. Here's something I find genuinely strange, and I'm not sure strange is a strong enough word, but let me try to say it plainly. The material in that cloud had been sitting there since before the sun existed. Some of it had been sitting there since before the stars that exploded to seed it with heavier elements. You are, in some measurable chemical sense, made of matter that has been in several different stars before this one. The iron in your blood was forged in a stellar core that no longer exists. The carbon, the oxygen, all of it cycled through processes so old that the word old stops meaning much. I think about that sometimes and then immediately stop thinking about it, because it's the kind of thought that gets heavy very quickly. But in the cloud, all of that material, all of that chemically complex previously stellar stuff was simply suspended, adrift, not going anywhere. And for a very, very long time, nothing asked it to. The shockwave changed the question. Not all at once, not everywhere. In one region of the cloud, the region that would eventually become this solar system, the compression created a knot of slightly higher density, and that knot began almost imperceptibly to pull itself together. It wasn't falling yet. It was tilting toward falling. There's a difference. The collapse when it came took about 100,000 years. Which sounds long, but in the timescale of everything we're talking about tonight, it is, and I want to be honest about this, almost nothing. A rounding error. The cloud that had existed for tens of millions of years spent roughly 100,000 of them actively collapsing into something new, and that 100,000 years was itself not a moment but a process, gradual and physical, full of competing pressures and conservation laws doing their quiet, insistent work. As the cloud collapsed, it spun. This is important. And it's one of those physics facts that sounds like it should have an explanation, like someone chose for it to spin, but it didn't have an explanation in that sense. It spun because the original cloud, across its enormous span, had tiny irregularities in its motion. Nothing moved perfectly. Different regions drifted at slightly different speeds, in slightly different directions. When all that material collapsed inward, those tiny differences added up. Angular momentum is conserved, which is a physicist's way of saying that the rotation that was spread across the whole cloud had to go somewhere when the cloud got smaller, so it concentrated, and the whole collapsing structure began to rotate faster as it shrank, like a skater pulling their arms in. Exactly like that, actually. The physics is the same, just the scale is somewhat different. The rotation mattered enormously because it's what prevented everything from collapsing into a single point. The infalling material settled into a disk, a wide, flat, spinning structure, thin in the middle and trailing off at the edges, with most of the mass concentrated at the center. At the center, what would become the sun, in the disk, what would eventually over tens of millions more years become everything else. But we're not there yet. Stay in the cloud for another moment. Before it became a disk, before it became a proto-sun and a proto-planetary disk, and eventually 8 planets and their moons and their rings and the asteroid belt and the Kuiper belt and the Oort cloud and everything else. Before all of that, it was still just material, just gas and dust. And the gas and dust didn't know what it was going to become. This sounds like a strange thing to say, because obviously matter doesn't know anything. But I mean it in a slightly different sense. There was nothing about the cloud at the moment before collapse that announced its future. No blueprint, no inevitability encoded in the arrangement. Just physical laws, operating on physical stuff, pushing it toward the configuration that the laws demanded. The solar system was not planned. it was solved for. The universe ran the equations, and all of this was the answer. I find that more beautiful than the alternative, though I'm not entirely sure why. There's a specific kind of quiet that comes before something organizing itself. Not silence exactly. The molecular cloud was not silent. If you'd been there with some instrument sensitive enough to detect it, you would have found it humming faintly with the radiation of early universe chemistry. But quiet in the sense of nothing yet committed, everything still in the space between states. The cloud would remain this way, enormous, cold, chemically inert in most of itself, waiting without intending to wait, until the shockwave arrived and pressed its thumb into one small region and said, in the language of physics, which is pressure and density and time, begin. It began. Not loudly, not dramatically. The collapse of a molecular cloud is not something you'd see from a distance the way you'd see a supernova. It's more like watching ice form on a lake. From far enough away you'd see nothing, just a surface. And then, much later, if you came back and looked carefully, you'd notice the surface had changed. Something had organized. Something was new. That's where we are at the end of this chapter. The cloud has tilted past the point of return. The collapse is underway. The material that will become the sun and the earth and the moon and everything you've ever touched is falling inward, slowly then less slowly, and arranging itself according to rules it didn't choose and couldn't refuse. The disk is forming. Somewhere inside it, heat is beginning to accumulate. And that heat, in 100,000 years or so, will do something that changes everything. If this kind of slow, careful science feels like something worth supporting, this is a self-funded project made without a studio or a team behind it. If you'd like to help keep it going, there's a link to the Patreon in the description. Gravity is not a dramatic force. I think that's the first thing worth saying, even if it slightly undermines the next several thousand words. It doesn't announce itself. It doesn't surge or flare or make a sound you could hear even hypothetically. It just, and this is almost frustrating, keeps being true. Keeps applying, keeps doing the same stubborn, indifferent thing it was doing a second ago and an hour ago and 1 billion years ago, with no variation, no mood, no interest in whether anything finds it convenient. And yet, here's what gravity was working with at the point where we left off. A collapsing molecular cloud, tens of light years across originally, now in the process of pulling itself inward along the axis of its own slight rotation. The material isn't falling the way something falls when you drop it. There's no clean arc, no single direction. It's more like everything is being nudged, everywhere all at once, toward everywhere else that has mass, which means toward the middle mostly because that's where most of the mass is accumulating. But not perfectly toward the middle. The rotation tilts everything slightly sideways, and what you end up with is not a ball but a disc, material spiraling in rather than dropping straight. Picture a drain, not a dramatic one, just the slow kind, in a sink that's almost empty, where the last bit of water traces wide, lazy circles before it narrows into the center. The solar nebula was doing something structurally similar, except the drain was gravity, and the water was a cloud of gas and dust spanning distances that make the word sink feel absurd. And the whole process took, roughly, accounting for the collapse phase, somewhere between 1 and 200,000 years. No, actually, I want to be careful here. The disk formation and the collapse aren't quite sequential. They're overlapping. The outer material is still drifting inward, while the inner material is already heating up, already thickening, already beginning to behave like something with a center. So it's less like watching a sink drain and more like watching a sink drain while someone is still running the tap. messier, more simultaneous. The image breaks if you press it too hard, and I should have said that before I used it. The centre. That's where the interesting pressure was building. As material fell inward, gas, dust, ice grains, silicate particles, hydrogen in every form it could take, it didn't just pile up tidily. It collided. At these densities and in full velocities, collisions between particles convert kinetic energy into thermal energy, which is a careful way of saying things crashing together make heat. And in the very centre of the collapsing cloud, things were crashing together constantly, relentlessly, with no space to dissipate the energy outward fast enough. The core got hot, not hot like an oven, not hot like anything in a kitchen or a foundry or a volcano, hot in a register that requires a different vocabulary, or at least a different sense of scale. Early on, during what astronomers call the protostellar phase before nuclear fusion begins, the central object reached temperatures of thousands of degrees, just from gravitational compression, just from the mechanical consequence of things falling and colliding and having nowhere to release the energy except as heat. There's something almost uncomfortable about that. You don't need a reaction, you don't need fuel, you just need enough stuff falling far enough, fast enough, into a small enough space. The universe will do the rest. Gravity charges no fee and requires no permission. What was forming at the centre had a name, technically a protostar. Though calling it a star at this stage feels premature, the way calling a city while it's still a collection of building materials and muddy ground feels premature. The protostar was hot and dense and continuing to accrete, to pull in more material from the disk around it, and it would continue doing this for somewhere between 100,000 and a few million years, depending on local conditions, before it crossed the threshold into something genuinely stellar. But I'm getting ahead of things. The disk is still forming. Let's stay there. Out beyond the hot, thickening centre, the disk was doing something I find, and I mean this without exaggeration, almost quietly remarkable. It was sorting itself, not by design, not by any process that wanted an outcome, but the physical conditions at different distances from the centre were different in ways that mattered enormously for what would eventually form where. Temperature dropped with distance. This sounds obvious, maybe even boring, but the consequence of that temperature gradient was that different materials could condense, could transition from gas to solid at different distances from the proto-sun. Close in, where temperatures were still brutally high, only things with very high melting points could survive as solids. Metal oxides, silicates, iron and nickel compounds. The stuff that would eventually go into building the rocky inner planets, Mercury, Venus, Earth, Mars, could only exist as solid particles in the inner disk, because it was literally the only stuff tough enough to hold together that close to that much heat. Farther out, past what planetary scientists call the snow line, roughly where Jupiter sits today, though the exact position shifted over time, water ice could exist. And once water ice could exist, a whole cascade of other volatiles could condense too. Carbon dioxide, methane, ammonia. Suddenly there was vastly more solid material available per unit of space, because you weren't limited to just the high-temperature resistant minerals. You had ice, you had organic compounds freezing out of the gas phase. The outer disk was materially richer than the inner disk, and that difference, that quiet, temperature-driven sorting of what could be solid where, is part of why the outer planets are gas giants and the inner planets are rocks. It's not because Jupiter won some competition, it's because Jupiter formed in a region of the disk where there was simply more buildable stuff. Gravity, meanwhile, was working at every scale simultaneously. This is the part I keep coming back to, the part that feels almost not quite philosophically troubling, but close. Gravity doesn't have a minimum scale. It doesn't wait until things are big enough to bother with. A dust grain exerts a gravitational pull on the grain next to it, a tiny, imperceptible, almost laughably small pull. But the pull is real, and if conditions are right, if the grains are moving slowly enough relative to each other, if they collide gently enough to stick rather than shatter, then they accumulate, they grow, and as they grow, their pull on surrounding material grows with them, which brings in more material, which increases the mass, which strengthens the pull. This is the mechanism that built planets, not one dramatic event, an accumulation of increments so small that none of them individually deserves a chapter. Dust grains stuck together and became pebbles. Pebbles, over time, and through a process that is still not entirely understood, there are things about this step that planetary scientists argue about, genuinely and unresolved, became planetesimals. Bodies maybe a kilometre across, maybe more, tumbling through the disk, gathering whatever came within reach of their modest gravity. A kilometre sounds large. In the context of what a kilometre-wide body eventually becomes, it is almost embarrassingly small. But gravity is patient in a way that nothing alive can quite be patient. It doesn't get tired, it doesn't lose interest. It keeps applying the same pull at the same rate, and time, given enough of it, does the heavy lifting. There's a texture to this process that I want to try and convey, even though I'm not sure I can. The disk at this stage, several 100,000 years into the collapse, planetesimals beginning to form in the outer regions, the inner disk still mostly gas and fine dust close to the growing protosun, was not an orderly place, it was turbulent. Eddies of gas moved through it, creating local pressure variations that could either concentrate solid particles or disperse them. Planetesimals in the same orbital region crossed paths and collided, sometimes merging, sometimes shattering each other back into gravel, the outcome depending on velocity and angle and the particular internal strength of each body. It was, and I want to find the right word here, not chaos exactly. Chaos implies randomness without structure. This had structure. It had the structure of physical law playing out simultaneously at every scale, in every direction, with every particle. It was more like noise that was secretly a signal, complicated and messy at the surface but with deep regularities running underneath, shaping the mess without being visible in it. The same gravity that was pulling gas into the protosun was also nudging planetesimals toward each other, also maintaining the broad circular motion of the disk, also, and this is something worth sitting with, already determining which orbital paths would be stable long-term and which would not. The disk was being pre-sorted by dynamics. Some orbits were safe, some were resonances that would be gradually swept clear. The solar system's basic architecture was being negotiated in the gravitational mathematics of the disk, millions of years before anything like a planet existed. I want to say something about scale, and I want to try to say it without the usual gestures toward how large everything is, because I think those gestures often produce the opposite of understanding. They produce a kind of numbing, a retreat into, well, it's very big, and then nothing more. So instead of scale in space, think about scale in time. The collapse phase, the molecular cloud pulling itself into a disk, took, as I mentioned, something like 1 to 200,000 years. That sounds long. Then the phase of planetesimal formation, dust grains becoming pebbles, becoming kilometre-scale bodies, took somewhere between 1 and 10 million years, depending on location in the disk. The phase of planet formation from planetesimals, the violent mergers, the runaway accretion, the final giants sweeping their orbits clear, took tens of millions of years for the inner planets, and longer for the outer ones. The Earth, as a recognizable body was mostly assembled within about 30 to 50 million years of the solar nebula's initial collapse. The moon-forming impact, the last major event that substantially changed Earth's mass and composition, happened somewhere around 40 to 60 million years in. 40 to 60 million years of building. And then, for the next 4.5 billion years, Earth has been sitting in more or less the same orbit, doing more or less the same thing. I don't know what to do with that ratio, honestly. The building took a fraction of a percent of the total time. The existence has been the rest of it. But the proto-sun is still growing, still accreting, still getting hotter. There's a threshold, the specific temperature and pressure conditions at which hydrogen nuclei can overcome their electromagnetic repulsion and fuse, and the collapsing core is moving toward it the way a slow freight train moves toward a junction. Without drama, without acceleration you'd notice from moment to moment, just steadily, inexorably getting closer to the condition that will change everything. The disk is spinning around it. Planetesimals are forming in the outer regions. The inner disk is still too hot, too turbulent, too thoroughly stirred by the proto-sun's radiation and magnetic field for much solid material to settle. And the core temperature climbs 1,000,000 degrees, 5 million, 10 million. At somewhere around 10 million degrees Kelvin, in the compressed chamber of what was once a cold, diffuse, entirely unremarkable cloud of interstellar gas, something happens, not an explosion, not a bang, something quieter and more fundamental than either of those words suggest. The fusion begins, and from that moment, the object at the center of the disk is a star, is our star, has been our star in some important sense ever since. That heat, what it means for the disk, for the forming planetesimals, for the question of whether anything close enough to the sun can survive what comes next, is where we're going. Not tonight, but soon. 10 million degrees. Say it quietly, don't perform it. Just let the number sit there for a second, because the temptation, and I feel it too, is to immediately reach for something to compare it to. The surface of the sun is 6,000 degrees. The surface of the Earth on a hot day is maybe 40. A candle flame is roughly 1400. The comparisons always fail at this scale, and I think the failure is instructive because what happened in the core of the collapsing proto-sun was not just more heat, it was a different category of physical condition entirely. A place where the word heat is technically accurate and practically useless. 10 million degrees Kelvin is the threshold, give or take. The temperature at which hydrogen nuclei, bare protons stripped of their electrons by the surrounding plasma, are moving fast enough, are packed densely enough that when two of them collide, they don't just bounce, they fuse. They overcome the electromagnetic repulsion that keeps like charges apart, and they get close enough that the strong nuclear force, which only operates at extraordinarily short range, can grab hold. And when it does, when that happens for the first time in the core of what was still technically just a very dense and very hot ball of gas, something changes, not loudly. That's what I keep wanting to say about this. The ignition of a star is not loud. It is not visible from outside for a long time. It is a change in what's happening at the center. And the center takes a while, thousands of years in some models, to communicate this change to the surface. The proto-sun didn't suddenly blaze. It reorganized quietly from the inside out. I want to say something about what fusion actually is before we go any further, because I think the word gets used in a way that makes it sound like burning, and it isn't burning. Burning is a chemical process, electrons rearranging between atoms, releasing energy from the reconfiguration of molecular bonds. Fusion is something else entirely. It is the combining of atomic nuclei into new, heavier nuclei, with the mass difference between inputs and outputs released as energy according to a relationship so famous it barely needs writing down. The energy released per fusion event is, and here I'm going to fumble for scale again, knowing the fumble won't quite work, roughly 1,000,000 times greater than the energy released per chemical reaction of equivalent mass. 1,000,000 times, not percent, times. So when the core of the proto-sun crossed that threshold and fusion began, the energy being generated per unit volume of that core increased by a factor that makes every previous heat source in the collapsing cloud look like a damp match. The gravitational compression that had been heating the core, which was already impressive, already producing temperatures in the millions of degrees, was joined by something fundamentally more powerful, and the core pushed back. This is the part I find almost, I want to say elegant, but that word has been used so many times in physics writing that it's gone a bit flat. What I mean is, there's a balance here that seems, from the outside, almost too convenient to be accidental. The fusion releases energy that creates outward pressure. That outward pressure resists further gravitational compression, which means the core doesn't collapse further, doesn't heat further, doesn't fuse faster in a runaway reaction. It stabilizes. The fusion rate adjusts to exactly balance the gravitational pull. The star finds an equilibrium, and then it holds that equilibrium. Our sun has held it for billions of years, but the disk doesn't know any of this yet. That's the thing about the interior of a star. The photons generated in the core don't just zip straight out. They're absorbed and re-emitted almost immediately by the surrounding plasma, shuffling outward in what amounts to an extraordinarily or random walk. In the sun, a photon generated into the core takes somewhere between 10,000 and 100,000 years to work its way to the surface. Maybe longer, the estimates vary, and the honest answer is that calculating it exactly is complicated by the sun's internal structure in ways that make confident numbers a bit slippery. So the disk, during the early period of fusion ignition, is not suddenly bathed in new light. The change is interior, hidden, and the disk is still doing its own thing. Dust grains accreting, planetesimals colliding, and occasionally surviving the collision, the inner region still turbulent and dense and hot from the ongoing infall of material. The disk at this stage had a quality, and this is where I want to be careful, because I'm about to use a word that implies more calm than was actually present, a quality of being very busy without looking like it from any distance. If you could somehow hover above it, at a remove of a few light hours, and watch the disk in some accelerated frame where 1,000,000 years took a minute, it would look like weather, complicated, churning, locally violent, broadly organized, spiraling arms of denser material, gaps being swept clear by the gravitational resonances of growing bodies, streaks of infalling gas still feeding the inner regions from above and below the disk plane. Not peaceful, not the serene flat ring it gets drawn as in textbooks. The protosun's radiation did eventually reach the disk, not through the slow photon diffusion from the core, through another mechanism. During the protostellar phase before and around the time of fusion ignition, young stars drive powerful outflows. Jets of material ejected along the rotational poles, and a broader wind of charged particles pushing outward in all directions. This is called, with the particular bluntness that physics sometimes achieves, the T Tauri wind, named for the class of young stars that exhibit it. And this wind started to do something to the disk that is, in retrospect, important in a way that feels almost deliberate, but wasn't. It started pushing the lighter material out. The gas, hydrogen and helium, the stuff that didn't condense into solid particles, began to be driven outward and eventually away from the inner disk. Not all at once, over millions of years, but gradually the inner solar system was being cleared of the gas that had been the bulk of the nebula's mass. What was left behind increasingly were solids. Dust, planetesimals, the seeds of rocky worlds, exposed now to the full, growing radiation of the young sun. The snow line matters here again. Inside it, where temperatures remained too high for ice, the solid material was mineral and metallic. Small, dense, not much of it comparatively. Outside it, in the colder outer disk, the gas giants were in the process of doing something different, building solid cores of ice and rock first, and then, because they were large enough, fast enough, using that gravity to capture gas directly from the disk before the stellar wind could sweep it away. Jupiter and Saturn were racing against the wind in a sense, and they won because they were big enough quickly enough. Uranus and Neptune, not quite. They got their cores built in time but were too slow accreting gas, too far from the centre, and ended up ice giants rather than gas giants. The distinction matters. The timing mattered. 10 million years earlier or later, and the outer solar system might look entirely different. There's something in the ignition of the sun that I haven't said yet, and I'm not sure how to say it without it sounding more meaningful than it is, or maybe less meaningful. I genuinely can't tell which direction the error goes. The moment fusion began in the proto-sun's core was the moment the solar system became, in some irreversible sense, organized around a single fixed point. Before ignition, the system was a collapsing cloud with a dense center, but the center was still accreting, still changing mass, still negotiating its own size. Once fusion balanced against gravity, the sun's mass was effectively set. Not exactly, it continued accreting for a while, but the central body had declared itself, had become the thing everything else would orbit. And the word orbit contains a lot. It contains the implication that nothing else would fall all the way in, that the planetesimals and protoplanets in the disk would be held at their respective distances, some of them anyway, by the balance of their own velocity against the sun's gravity. The sun had become, in the most physical sense of the phrase, the center of something. I find this, and I want to be honest that I'm not sure find is quite the right word. This is more something that happens to me when I think about it for long enough. I find this strange, that the entire architecture of everything we live within, all the nested orbits and gravitational relationships that make the night sky what it is, descends from a threshold, crossing in a hot plasma that happened 4.5 billion years ago. That the sun igniting was the moment the solar system stopped being a process and started being a place. The disk responds to ignition slowly, fussily almost. The inner regions closest to the new radiation source get hotter. Some materials that had begun to condense into solid particles get re-evaporated, pushed back into the gas phase, forced to wait until they drift slightly farther out before they can condense again. The boundary between what can be solid and what must be gas shifts outward with the increasing luminosity. The whole inner disk is being rearranged, chemically, by the young sun's growing output. Farther out, things are more insulated from this. The outer disk continues its slower processes, largely indifferent to the drama in the inner regions, though the stellar wind is beginning to thin the gas at all distances. The clock for gas giant formation is running. Solid cores in the outer disk are pulling in ice and rock growing, approaching the mass threshold at which they can start to gravitationally capture hydrogen and helium directly. Somewhere in the middle distance, in the region between where the rocky stuff ends and the icy stuff begins, the region that will eventually be the asteroid belt, things are getting complicated. Material from inside the snowline and material from outside it are mixing, getting stirred by the gravitational influence of the growing outer protoplanets. The asteroid belt will never form a planet, not because there isn't enough mass There isn't much, but there was more once. But because Jupiter's gravity will keep that region perpetually stirred, preventing accumulation from reaching the scale needed for a proper planetary body. Jupiter again. Jupiter keeps mattering, but that's a later chapter. What I want to end with, what this chapter has been slowly arriving at without quite announcing it, is something about the nature of what the ignition changed. Before fusion, a hot, dense, still accreting protostar. Gravity dominant, energy coming from compression alone. After fusion, a star, a thing with an internal energy source that will last, in our Sun's case, for roughly 10 billion years total, of which it has used about 4.5. The change is not visible from outside for a long time, but it is the change that made everything else possible. Not life. That's much later, and much more contingent, and involves a long chain of accidents that have no guarantee anywhere in them. But the stable platform that life would eventually, improbably us, the Sun's equilibrium, fusion balancing gravity, is what gives the solar system the thing it needed most. Time, not drama, not energy exactly, though the energy matters. Time, stable, consistent, long-stretch time, during which the disk could finish its work, the planets could settle their orbits, the surfaces could cool, the chemistry could proceed at whatever pace chemistry proceeds at when no one is rushing it. The Sun ignited, and then it just kept going. Steadily, without variation you'd notice on any human timescale, burning through its hydrogen at a rate calibrated, not deliberately, just physically, to make the light last. It is still doing it now while you are lying here. The same reaction, the same balance. 4.5 billion years later, and the core is still fusing hydrogen, still pushing back against gravity, still making the 8 minutes of travel time between that core and your window worth something. The disk is still out there, of course, long since resolved into planets and debris in the cold distances of the outer system. But the sun that lit it is the same sun, slightly brighter than it was at ignition actually. It has been gradually brightening over its lifetime, and will continue to do so, which matters later in this story in ways that are not comfortable to think about at bedtime. But that's later. For now, the star is lit, the disk is spinning, the first solid bodies are beginning to matter to each other gravitationally, and somewhere in the outer disk a core of ice and rock is getting large enough to start pulling in gas, getting large and heavier and harder to ignore. Nobody built the planets. That sounds obvious when you say it, but I think it's worth sitting with for a moment, because the way we talk about planetary formation, the way I've been talking about it probably, carries a faint implication of construction, of process with direction, material gathering because it was supposed to gather, bodies forming because the solar system had something like a plan for them. It didn't. There was no intention anywhere in the disk, just physical law operating on physical stuff, producing outcomes that nobody specified and nobody could have predicted in detail, even with perfect knowledge of the starting conditions. The planets accreted. That's the word. It means more or less that things stuck together over time and the sticking compounded on itself. And the reason I want to start there, with the absence of intent, is that the actual process of accretion is so slow, so incremental, so utterly devoid of drama at any individual moment, that the only way to find it interesting is to let go of the idea that interesting things have to happen quickly. This chapter is about patience. Not the human kind, which is always tinged with waiting and wanting. The other kind. The kind matter has when it has no preference either way. Start small, smaller than small, start with a dust grain. In the protoplanetary disk, roughly 4.5 billion years ago, there were a lot of dust grains, an amount that doesn't really have a useful number attached to it. The disk's total solid mass was perhaps a few % of the Sun's mass, spread across a volume of space extending tens of astronomical units in every direction, and most of that mass was in particles smaller than a human hair is wide: silicate grains, iron particles, carbon compounds, ice-coated mineral fragments in the outer disk, beyond the snowline, where temperatures were cold enough to let water freeze onto surfaces. Each of these grains was moving, orbiting the Sun technically, though on paths so similar to their neighbours that orbiting together is more accurate. And they collided. Constantly, probably. The disk was dense enough in its early phases that any given grain encountered other grains frequently. Most of those collisions were, and here's where the process gets fussy, genuinely fussy in a way that took planetary scientists a long time to work out, not catastrophic, not violent, just two small things touching at low relative velocity, with nothing to make them bounce very hard, and sometimes, not always, not even most of the time, but sometimes, they stuck. The sticking is the part I used to gloss over in my own head, as if it were obvious. It isn't. Why would a silicate grain stick to another silicate grain? There's no glue, no molecular affinity strong enough at first glance to explain why collision equals adhesion. The answer, and it took a lot of careful laboratory work and a lot of modelling to get here, involves van der Waals forces, which are weak electrostatic attractions that operate between neutral molecules at a very short range. They're the same forces that let geckos walk on ceilings. The gecko thing is real. I mention it because it always surprises people, and also because it's the kind of detail that makes the universe feel like it was designed by someone with a very specific sense of humour, which it wasn't, but still. At the scale of dust grains, van der Waals forces are enough. Two grains collide softly, their surfaces get close enough that these weak forces activate and they stick. Not strongly. You could separate them with almost no effort if you were somehow there to try, but they stay together because nothing is trying to separate them. The disk is not rough with them. They drift in the same orbital path and encounter no strong turbulence at their scale, and so the bond holds. A two-grain clump then collides with the third grain, sticks, then another. Then two clumps find each other and merge. The structure is fluffy, genuinely fluffy, like aggregated soot, full of empty space and fragile connections, but it's bigger than a single grain, and bigger matters eventually, even if it takes a very long time for eventually to arrive. I want to stop here and be honest about something. The step that comes next, the transition from centimetre-scale fluffy aggregates to metre-scale bodies, and from metre-scale bodies to kilometre-scale planetesimals, is not fully understood. The honest answer, the one that doesn't get said enough in popular science writing, is that this is an active area of research, and the models don't agree perfectly, and there are real problems that haven't been solved cleanly. The most stubborn of these problems has a name, the meter-size barrier. As clumps grow from millimetres toward metres, something changes. Larger aggregates moving through the disk interact with the gas differently. They drift inward toward the Sun faster than small grains do, because of a pressure differential in the disk gas that acts like a headwind at this particular scale. A meter-sized body spiralling inward might fall into the Sun in just a few hundred years, which is, in geological terms, immediately. Far too fast for meter-sized things to grow into kilometre-sized things through simple collision. So how did planetesimals form at all? The leading candidate, the mechanism that most current models favour, is something called streaming instability. In certain conditions, solid particles and gas in the disk can self-organise. The solid particles concentrate into dense filaments or clumps, locally increasing the solid-to-gas ratio enough that gravity takes over. The clump collapses directly into a planetesimal, maybe kilometers across, without needing to pass through the vulnerable meter-size phase 1 grain at a time. Which means, and this is the part that surprised me genuinely when I understood it clearly enough, that some planetesimals may have formed not by gradual accumulation, but by a kind of gravitational shortcut, bypassing the slow grain-by-grain process for the regions of the disk where conditions were right for streaming instability, going from pebble-sized particles to kilometre-scale bodies in what by disk timescales was almost a jump. Almost, not quite. The details are still being worked out, and different research groups get somewhat different answers depending on their assumptions about disk turbulence and particle size distribution and gas density, and I'm going to stop there, not because it isn't interesting, but because the uncertainty is the point. The solar system formed. That is not in question. Exactly how it got through this particular bottleneck is still, to some degree, open. Once you have planetesimals, bodies ranging from roughly a kilometre to maybe a few hundred kilometres across, the physics shifts register entirely, because now you have gravity, real meaningful, full, object-level gravity, not the van der Waals fuzz of dust grain adhesion, not the streaming instability's statistical self-organization, actual gravitational wells pulling in surrounding material growing with each addition. Pick up a handful of river gravel sometime and feel the weight of it. The smoothness of individual stones, the way they knock against each other with that specific dense sound. A planetesimal is not much more than that at first, a loosely bound rubble pile of mineral and ice tumbling slowly in the disk, occupying a particular orbital path. Not impressive, individually. Not large enough to be round. The smallest planetesimals were lumpy, irregular, shaped by whatever collisions had assembled them. But they were pulling, gently, constantly, without rest, and the disk around them was full of smaller material drifting in similar orbits, occasionally crossing their path. When a pebble or a small aggregate drifted close enough to a planetesimal, it felt that pull. Didn't feel it the way you or I feel gravity. Didn't feel it at all in any conscious sense, but responded to it the way mass always responds to mass. Curved toward it, slowed, fell in. The planetesimal grew. Its gravity grew with it. Its ability to capture more material grew with its gravity. This is what planetary scientists call runaway accretion, a feedback loop in which growth accelerates growth, where the biggest objects in a region of disk pull material away from smaller competitors and grow faster than those competitors can, ensuring that the big get bigger at an accelerating rate while the smaller bodies are effectively starved. It is, and I want to be careful about how much personality I assign to a gravitational process, almost opportunistic. The large planetesimals in a given region of disk were not trying to become planets. They were just better at accumulating mass than smaller bodies were, and the disk rewarded that mechanical advantage with more mass, which made them more advantaged, which gave them more mass, until something. Until they ran out of material in their orbital neighborhood, or until they grew large enough to gravitationally interact with bodies in neighboring orbits, or until they collided with something comparable in size, and the collision was violent enough to matter in a different way. That last one, that's important. The late stages of rocky planet formation, the final assembly of the inner planets from a population of protoplanets, bodies that might be the size of Mars or larger, moving on orbits that had become increasingly chaotic as their mutual gravitational influence grew, involved impacts of a scale that is genuinely difficult to hold in mind. Not the gentle collisions of dust grains, not even the modest mergers of early planetesimals. World-sized objects hitting world-sized objects at velocities of kilometers per second, releasing energies that melted the impacted bodies entirely, resetting their surfaces, mixing their interiors, sometimes launching enormous quantities of material into orbit. The Earth was hit like this, more than once probably during its assembly, but once in particular late in the process, by a body roughly the size of Mars, in an impact so energetic that it threw enough material into Earth's orbit to form the Moon. We'll get to that. It has its own chapter, because it deserves one. The point for now is that the planet formation process was not quiet at its end. The patient accumulation of dust grains, the slow growth of planetesimals, the gradual runaway accretion of protoplanets, all of that patience, all of that incremental work, eventually produced bodies large enough to collide catastrophically. The quietest process in the solar system's early history, taken to its conclusion, produced the loudest events. I'm not sure what to make of that. Maybe nothing, maybe it doesn't make anything. The outer solar system was doing its own version of this simultaneously, in the same general period, but with different materials and different outcomes and a different pace. Beyond the snow line, where ice was available as a building material, solid cores grew faster and larger than their inner disk counterparts. Jupiter's core, ice and rock, assembled from the relative abundance of solid material in the outer disk, reached somewhere around 10 to 20 Earth masses before something tipped. And when a solid body in the disk reaches that mass, the game changes completely, because now it has enough gravity to hold on to gas, not just solid particles drifting past, actual hydrogen and helium from the disk, the gas that the stellar wind hadn't yet fully cleared from the outer regions. The core starts pulling it in, and once the gas accretion starts, it accelerates. Jupiter went from a solid core of maybe 15 Earth masses to a total mass of 318 Earth masses in, the models suggest, perhaps just a few million years. That is fast by the standards of everything else we've discussed. Startlingly fast. The inner solar system spent tens of millions of years assembling its rocky planets. Jupiter essentially collapsed into itself, gas pouring onto a solid core in a fraction of that time. And Jupiter's rapid growth mattered for everything else, not just because of what it became, but because of what it did to the disk around it. A body that massive, growing that quickly, creates ripples in the disk, pressure waves, compositional disturbances, gravitational resonances that propagate outward and inward and clear certain orbital regions and stir others. Jupiter's formation was not a contained event. It was a disturbance, a reorganization. The disk felt it. Everything in the disk felt it, in the slow language of changed orbital dynamics and redistributed material. And Jupiter wasn't done yet. It was about to move. But before we follow Jupiter, before we trace the strange inward migration that would reshape the inner solar system in ways that still matter tonight, there's something I want to stay with for another moment. The dust grains. I keep coming back to them, and I'm not entirely sure why. Maybe because they're the beginning of something so improbably large. Maybe because there's something almost tender about the van der Waals fuzz, the weak and fragile adhesion of two silicate grains in a cold, indifferent disk, that somehow, given time, given the compounding of increments, given nothing more than physical law and the absence of anything strong enough to undo what was being done, eventually became this, a planet, an ocean, the specific weight of river gravel in your palm, which is made of minerals that were once those grains in that disk, adhering to each other in the dark. I don't think that's a poetic observation. I think it's just a true one. The grains didn't know, the disk didn't know, gravity didn't know, and yet here we are, made of the compounded result of 4.5 billion years of things just barely holding together. There's a sound that old houses make at night, a soft settling of wood and plaster that has nothing to do with anything threatening, just the structure adjusting to the temperature drop. I used to lie awake listening to it as a kid, not scared exactly, just aware that the building around me was doing something I couldn't see. That's the closest analogy I have, and I know it doesn't quite reach, but the early solar system felt to me like that. Quiet, complex, full of invisible adjustments, each one trivial, the sum of them everything. The dust settled, and kept settling, and in the settling, over time and without ceremony, it became. There is a version of the solar system, not a hypothetical one, not a science fiction one, but a version that the physics of the early disk made genuinely plausible, in which Jupiter migrated all the way inward and kept going, in which it fell toward the Sun, consuming the material of the inner disk as it went, eventually settling in an orbit where Venus is now, or Mercury, or the models allow for it, even closer. In that version, there are no rocky inner planets, no Earth. The inner solar system is Jupiter's territory, and whatever formed in its wake, if anything did, would be small and strange and nothing you'd recognize. That version almost happened. I want to be careful about the word almost. Astrophysics is not a field that deals in near misses with the emotional weight that implies. Nobody was watching, nothing was at stake in any felt sense. But the dynamics were genuinely poised. Jupiter migrated inward for a significant fraction of the distance it would have needed to cover to eliminate the inner solar system, and it stopped because of Saturn. And Saturn's arrival was not inevitable. It was the consequence of Saturn forming fast enough, in the right orbital relationship, at the right moment in the disk's lifetime. Change any of those variables by enough and the outcome changes. So, Jupiter moved. Let's talk about that. Planets migrate. This took a long time to become accepted, and even after it was accepted, it retained a slightly uncomfortable quality in planetary science. The sense that the solar system we observe, with its tidy orbital spacing and its rocky inner planets and its gas giants, parked respectfully far out, had always been more or less as it appears. Migration disturbs that picture considerably. It says, the planets are not where they formed. Some of them are nowhere near where they formed. The solar system's current architecture is not its original architecture. Jupiter formed, the best current models suggest, at somewhere around 3 to 5 astronomical units from the Sun, roughly where it sits today, give or take. But the disk it formed in was full of gas, dense, structured, swirling gas, and a body as massive as Jupiter doesn't simply sit in a gas disk without interacting with it. Its gravity creates waves in the disk, spiral density waves, perturbations that carry angular momentum outward from Jupiter and deposit it in the outer disk, while simultaneously pulling angular momentum from the inner disk and depositing it into Jupiter. The net effect of this exchange under the conditions of the early disk was to push Jupiter inward. Not quickly, this is not an avalanche, it's more like, and here's the metaphor I want to use, knowing it'll break if pressed too hard. It's more like placing a heavy object on a waterbed. The object doesn't fall, it sinks slowly, the surface deforming around it, the pressure redistributing. Jupiter in the disk sank inward the same way, gradually, measurably if you were watching over the right timescale, and as it moved, it did not move cleanly through empty space. It moved through a disk full of material. What Jupiter did to that material is where the story gets genuinely complicated and genuinely consequential. As Jupiter migrated inward, past 4 astronomical units, past 3.5 toward 3, its gravitational influence swept through the region that would eventually become the asteroid belt. And swept is almost too gentle a word. Barged, maybe. Sort of bulldozed, while simultaneously scattering material in 2 directions at once, some of it flung inward toward the sun and some of it kicked outward into the cold. The primordial asteroid belt at this point likely contained far more mass than it does today, possibly several times the mass of Earth, spread across that orbital region in planetesimals and small protoplanets that had been quietly accreting. Jupiter's passage reduced it. Not all at once. The gravitational resonances it established as it moved through and then past the belt were the main mechanism. Orbital relationships between Jupiter's period and the periods of belt objects that created regular gravitational kicks, steadily pumping up orbital eccentricities until objects crossed each other's paths, collided, shattered, or were ejected entirely. The belt was being stirred in a way it had never been stirred, and stirring at that scale is not gentle. Most of what the belt contained was lost, flung into the inner solar system onto sun-crossing orbits, into collisions with the growing rocky protoplanets, or thrown outward past Jupiter into the outer solar system and beyond. The asteroid belt today contains roughly 4% of 1% of Earth's mass. Compared to what was there before Jupiter's migration, it is an almost empty room. That's not a metaphor. It's close to literally true. Meanwhile, inward of the belt, the inner solar system was being rearranged by Jupiter's approach in ways that are still being modelled, still argued about, still producing subtly different answers depending on which research group is running the simulation. What's broadly agreed? Jupiter's inward migration compressed the disk of rocky material in the inner solar system, pushed it, herded it. The gravitational influence ahead of the planet's inward path drove material toward the sun, concentrating it into a tighter, denser annulus closer in. This compression matters enormously for what the inner planets eventually looked like. Mars, which sits at the outer edge of the inner solar system, ended up small, about 1/10 of Earth's mass, partly because Jupiter's migration starved the Mars-forming region of material. The stuff that would have built a larger Mars was pushed inward or scattered outward. Mars, in other words, is small partly because Jupiter was heavy and oblivious and passed too close. Mars has been dealing with the consequences of that for 4.5 billion years and will continue to do so indefinitely. I don't think Mars minds, but I find myself minding slightly on its behalf. Now, Saturn. Saturn was forming in the outer disk while all of this was happening, growing its own solid core accreting gas, becoming the second largest body in the solar system, and migrating inward too, because Saturn was also embedded in the disk, also subject to the same disk torques that were pushing Jupiter. But Saturn is less massive than Jupiter, and less massive planets migrate at different rates through disk gas, and Saturn was catching up to Jupiter rather than moving in lockstep with it. When Saturn reached a particular orbital ratio with Jupiter, close to a 2:3 resonance where Saturn completed 2 orbits for roughly every 3 of Jupiter's, something changed in the disk dynamics. The torques that had been pushing Jupiter inward reversed. Not immediately, not all at once, but the combined gravitational influence of the 2 planets on the disk around them shifted the balance of angular momentum exchange. Jupiter stopped sinking inward, and then, gradually, both planets began moving outward together. This reversal is the grand tack, named for the sailing maneuver, the tack, in which a boat turns into the wind and reverses its course. Jupiter tacked, somewhere around 1.5 astronomical units from the Sun, roughly where Mars is today, roughly half the distance Jupiter had travelled inward. The migration reversed, and Jupiter and Saturn moved outward, together, slowly, stopping eventually near their current positions as the disk dissipated and the gas that had been driving the migration thinned and finally cleared. The inner solar system that Jupiter left behind was not the inner solar system it had found on the way in. It was depleted, stirred. The belt region was largely emptied, and importantly, this is the part that took me a while to appreciate fully, it was reseeded on the way out. As Jupiter and Saturn moved outward through the belt region again, their gravitational influence captured some outer solar system material, ice-rich, carbon-rich objects from beyond the snowline, and delivered them into the belt. Which is why the asteroid belt today has two broad populations of objects: the drier, rockier type asteroids in the inner belt, relics of the original inner solar system, and the darker, more chemically primitive C-type asteroids in the outer belt, which came from much farther out and were deposited there by the outward migration. The belt is not just leftover debris from planet formation, it's a mixed archive, a geological record of where things came from and what moved them. I find that genuinely remarkable. The asteroid belt is a record of Jupiter's migration, readable in the chemical composition of objects that have been sitting there, mostly unchanged, for 4.5 billion years. We have meteorites from C-type asteroids in laboratories on Earth right now. We can measure their chemistry, and the chemistry tells a story about where they formed and how they got to the belt, and the story is consistent with the grand tack, that's not nothing. That's the solar system leaving a receipt. There is a version of this story that I want to tell but can't quite, because the honest answer is that the grand tack model, while compelling and widely discussed, has critics. Some planetary scientists argue that it relies on assumptions about disk conditions that may not be well constrained. Alternative models for the low mass of Mars and the structure of the asteroid belt exist, and some of them don't require Jupiter to migrate inward at all, or require it to migrate much less dramatically. The picture is, and I want to resist the temptation to tie this too neatly, genuinely unsettled at the edges. What is not unsettled? Jupiter migrated. The evidence for planetary migration in general, from exoplanet populations, from the orbital structure of the outer solar system, from the compositional gradients in the asteroid belt, is robust. The exact path Jupiter took, the extent of its inward excursion, the timing relative to Saturn's influence, these remain areas where the models don't fully agree. I mention this not to undermine what came before, but because I think the honest uncertainty is part of the story. The solar system formed 4.5 billion years ago. We're working backward from what we can observe now, the planet's orbits, the belt's composition, the chemical signatures and meteorites, and doing our best to reconstruct the path. The reconstruction is good. It's not complete. What Jupiter's journey left behind, beyond the reorganized belt and the depleted Mars region, was an inner solar system with a specific architecture. A small, tight annulus of rocky material from which 4 planets would form: Mercury, Venus, Earth, Mars, each of them shaped in part by the disturbance Jupiter had caused, each of them sitting on the orbits that Jupiter's passage had made available. Earth, specifically, ended up in a position that would matter enormously later. Not too close to the Sun, not too far. In the zone where water could exist as liquid on a surface where temperatures were not too high for complex chemistry, where the gravity was sufficient to hold an atmosphere but not so large as to hold the wrong kind. This is the part where some people want to reach for the word coincidence and others want to reach for the word inevitable, and I honestly don't know which is right. Maybe neither. Maybe the framing of coincidence versus inevitability is the wrong frame for a system this old and this complex. What I know is that Jupiter moved and turned and moved back, and in the space it left behind, in the material it compressed, and the orbits it cleared, and the belt it stirred, and the outer solar system it reorganized, the conditions for everything that followed were set, not determined. Conditions aren't determinations, but narrowed, made more specific. Jupiter's migration took an enormous range of possible solar systems and reduced it to something closer to this one. Whether that's remarkable or just physics probably depends on what you think remarkable means. I find it remarkable, but I acknowledge that I am standing inside the outcome. The disk is quieter now than it was. Not quiet. The late stage of planetary assembly is still producing enormous collisions in the inner solar system. The rocky protoplanets still merging and shattering and remerging in the slow, catastrophic grind of final accretion. But Jupiter has settled. Saturn has settled, near its current distance, in an orbital relationship with Jupiter that would remain dynamically important for billions of years. The outer solar system still has adjustments to make. Neptune hasn't yet migrated to its final position, and the Kuiper belt hasn't yet been sculpted into its current configuration, and there is a period of late heavy bombardment coming that will leave its mark on every solid surface in the inner solar system. But the largest gravitational presence, the one that did the most to shape what the inner solar system would become, has done its most dramatic work. Jupiter is where it roughly will be now, watching or not watching, being massive in a particular place which has the same effect. The inner solar system continues its own assembly in the long aftermath of the giant's passage. Rocky bodies colliding, protoplanets merging, surfaces melting and cooling and differentiating, iron sinking to cores, lighter silicates floating upward, as gravity sorts the interiors of growing worlds by density. Somewhere in that process, on one particular protoplanet in one particular orbit, an impact is coming. One that will change the surface and the sky and the night. That one deserves its own chapter. Look up tonight if you haven't already. Or don't. The ceiling is fine and the moon isn't always visible, and this isn't that kind of chapter, but hold it in mind. The moon. That specific pale presence, familiar to the point of invisibility most nights. The thing you've navigated by and ignored and occasionally actually looked at. Hold it there. Now consider that it shouldn't exist, not in any dramatic sense. I don't mean the universe was trying to prevent it. I mean that if you ran the physics of the early solar system forward from its initial conditions, the moon is not an obvious outcome. It requires a very specific thing to happen, at a very specific time, in a very specific way. And that thing is an impact. A collision between the early Earth and another planetary body roughly the size of Mars, at an angle and velocity that sits inside a surprisingly narrow window of outcomes, too fast or too slow, too head-on or too glancing, and you don't get a moon. You get something else or nothing at all. The collision happened anyway, somewhere around 40 to 60 million years into the solar system's history, which sounds like a long time but is roughly 1% of the Earth's current age. An object hit the early Earth, and the solar system has had a moon ever since. The object is called Theia, which is a name from Greek mythology, the Titan goddess who was the mother of Selene, goddess of the moon. It is a graceful name for something that was, in all likelihood, a graceless object. A protoplanet, assembled from the same disk material as Earth, growing in an orbital region that overlapped enough with Earth's gravitational influence that the two bodies couldn't ignore each other indefinitely. Theia wasn't a rogue visitor from outside the solar system, it was local. A neighbour that had been accreting in the same general orbital neighbourhood for tens of millions of years, slowly accumulating mass, and slowly, through the long negotiation of mutual gravitational influence, drifting onto a path that would eventually intersect. How large was Theia? Mars-sized is the estimate most often cited, which puts it at roughly 10 to 15% of Earth's current mass. Not small, not a pebble, a genuine planetary body differentiated, meaning it had been large enough and hot enough for long enough that its interior had separated by density, iron sinking to a core, silicate rock floating to form a mantle. It had a structure. It was, in some meaningful physical sense, a world, and it hit us. The reconstruction of what happened in those first minutes is based on computer simulations, on the chemical analysis of lunar rocks, on the specific ratios of isotopes in Earth's mantle and the Moon's crust, on angular momentum calculations that have to be made to balance. It is not a simple story, and the details have changed as the models have been refined. The current best understanding is actually somewhat different from the version I learned first, and I suspect it will continue to be refined because the impact happened 4.5 billion years ago, and we are working backward at from incomplete evidence. But here is what the models broadly agree on. Theia struck the early Earth at an angle, not head-on, not perfectly glancing, somewhere between those. The relative velocity was probably in the range of a few kilometers per second, which sounds modest until you remember that Theia was roughly Mars-sized, and the kinetic energy of impact scales, with both mass and velocity squared. And the numbers that fall out of that calculation are so large they stop feeling like numbers in any useful sense. The collision took, in terms of the initial contact and primary energy release, minutes, not hours. Minutes. In those minutes, the energy delivered to the impact site was enough to vaporize rock. Not melt it, vaporize it, turn solid silicate material directly into plasma and gas. A superheated plume expanding outward from the impact point at velocities that would have carried it across the entire surface of the early Earth in hours. The impact didn't punch a hole in the Earth, and I'm going to use a low register word here because the technical vocabulary doesn't convey the physical reality any better. Smeared. Both objects, Earth's mantle and Theia's mantle, were violently mixed, thrown partly outward into space, partly redistributed across Earth's surface, partly kept in the growing, reshaping body of the post-impact Earth. The iron cores, Earth's and Theia's, merged. This is one of the things the models are fairly confident about, and it has a consequence. The Moon, which formed from the material thrown into orbit by the impact, is depleted in iron relative to Earth. The cores merged and stayed. The mantle material went into orbit. The Moon is, in chemical terms, made largely of what used to be the outer layers of two planets, thoroughly mixed, thrown up, and then condensed from a ring of debris into a single body. That process, the condensation of the debris ring into the Moon, took perhaps a few hundred years, maybe 1,000, geologically, immediately. The Moon that formed was not the Moon you hold in your mind when you look up. It was closer, much closer. The current models suggest it may have been, and here the estimates have a real spread, so I'm going to be honest about the uncertainty, somewhere between 15 and 30 times closer to Earth than it is now, which would have made it enormous in the sky. Not the comfortable silver disk we have. Something that would have dominated the sky, visibly large even in daylight, raising tides on the early Earth's surface. If the early Earth had a surface in any meaningful sense, which it barely did, there were hundreds of times the height of modern tides. The Moon has been moving away from Earth ever since. Tidal friction, the gravitational interaction between the Moon's pull and Earth's rotation, working through the oceans and even the rocky body of the Earth itself, transfers angular momentum from Earth's rotation to the Moon's orbit. Earth's rotation slows, the Moon moves outward. Both of these things are happening right now at this moment as you lie here. The Moon is moving away from Earth at roughly 3 to 4 centimeters per year. The days on Earth are getting very, very slightly longer. These rates have not been constant throughout history. They depend on the distribution of continents, the depth of oceans, the geometry of coastlines, and all of those have changed enormously over 4.5 billion years. So reconstructing exactly where the Moon was at any given past date is genuinely complicated. I'm going to leave that thread there and not pull it, because it leads somewhere quite deep, and this is already a heavy chapter. The early Earth, in the aftermath of the impact, was not a place, not in any sense you'd recognise. The surface, to the extent it had a surface, was molten. The energy of the impact had been enough to melt the entire outer portion of Earth's body, producing what geologists call a magma ocean, not a metaphor. An ocean of liquid rock covering the planet kilometres deep, slowly cooling from the top as heat radiated into space, slowly being stirred from below by convection. The early atmosphere, to the extent there was bound toward one, was mostly silicate vapour and outgassed volatiles, water, carbon dioxide, sulphur compounds, a thick, hot, opaque shroud that let in almost no sunlight and would have made the surface, if you could somehow stand on it, smell like something between a volcano and the inside of a kiln. There is a particular quality to the smell of hot stone in summer, the specific dry sharpness of a sun-baked rock after rain. I think about that smell sometimes when I'm trying to hold the early Earth in mind. Except hotter. Except more total. Except covering everything. Cooling took time. The magma ocean solidified gradually, the first solid crust forming, being broken and remelted, forming again, building up slowly over tens of millions of years. Water, delivered partly by the outgassing of the solidifying mantle, and partly by incoming comets and asteroids, began accumulating. The atmosphere thickened, then changed character as the temperatures dropped enough for water vapour to condense. At some point, and determining when exactly, is one of the harder problems in early Earth geology, because the evidence is so old that most of it has been destroyed by subsequent geological activity. Liquid water pooled on the surface, and stayed. The oldest material we have that preserves a chemical record of early Earth's conditions is zircon. Tiny crystals, some of them barely the width of a human hair in their smallest dimension, found in ancient metamorphic rocks in Western Australia. The oldest of these zircons dates to roughly 4.4 billion years, and the chemical signatures preserved in those crystals, specifically the ratios of oxygen isotopes, suggest that liquid water was present at or near the surface when they formed. 4.4 billion years ago, less than 200 million years after the moon-forming impact, on a planet that was, by any reasonable geological assessment, still in the process of cooling from an ocean of molten rock. I find this, and I want to be careful about how I say this, because I don't want to reach for the word remarkable when I mean something more specific. I find this almost difficult to accept, so, even knowing the physics allows it. The Earth was still cooling from the most violent event in its history, and water was already pooling on its surface. The path from magma ocean to liquid water was short enough, geologically speaking, that the two conditions nearly overlap. If you'd like to go deeper, there are research notes on this chapter available on Patreon. The link is in the description. What the moon did to the early Earth, beyond the obvious violence of its formation, is a question that planetary scientists keep returning to and keep finding new angles on. The moon stabilizes Earth's axial tilt. This is one of those facts that is often cited and rarely fully absorbed. Earth's axis is tilted about 23.5 degrees relative to its orbit around the Sun, and this tilt is what gives us seasons. Without the moon's gravitational steadying influence, that tilt would wander chaotically. Models suggest it could vary anywhere from nearly 0 to perhaps 85 degrees over millions of years, driven by the gravitational perturbations of the other planets. A tilt of 85 degrees would mean the poles pointing almost directly at the Sun for half the year. Climate instability so extreme that it's difficult to model what life could have done with it, if anything. The moon holds the tilt steady, within a small range of variation over the timescales that complex life requires. The Earth's seasons stay seasons, reliable enough to be planned around, consistent enough for the slow work of evolution. The moon also contributed to tidal rhythms, which some researchers believe played a role in the emergence of early life. The intertidal zone, alternately flooded and exposed, a chemically concentrated, energetically complex environment. Maybe, probably. The moon's role in early life is not settled, and I want to leave it unsettled rather than overstate it, but I want to come back to where I started. The moon in the sky. That specific pale, familiar presence. It formed from a disaster, from an impact so violent it melted two planets simultaneously, mixed their interiors, threw enough material into orbit to build a new world from scratch. It formed quickly geologically from a ring of vaporized rock and shattered mantle material. It was huge and close and covered the early sky in a way that would have been, if anyone had been there to see it, not beautiful so much as overwhelming. And then it spent 4.5 billion years moving away, slowly 3 to 4 centimeters per year, so slowly that no individual human life, or 10,000 individual human lives stacked end to end, would register the change. But it's moving, right now. This moment, while you are lying here with the ceiling above you or the window dark beside you, the moon is 3 to 4 centimeters farther from Earth than it was a year ago. The same moon, the one formed in a collision that should not have produced something so stable, so permanent feeling, so, given what made it, so quietly present. It shouldn't exist. And yet here it is, drifting steadily away, and here we are, not noticing. Nobody knows exactly where the water came from. That sentence deserves to sit alone for a moment, because it tends to get buried inside more confident-sounding paragraphs about isotope ratios and delivery mechanisms and competing hypotheses. But the honest version of the story starts there. The origin of Earth's water is an open question. Not wide open. There are strong candidates, real constraints, evidence pointing in specific directions, but not closed, not settled. The textbook answer doesn't exist yet, and the people working on it will tell you so. What we know, water is here, has been here in liquid form on the surface for somewhere close to 4 billion years, possibly 4.5. And it arrived or emerged, depending on which mechanism you favour, on a planet that was, not long before, a magma ocean, hot enough to vaporise rock, hostile to liquid anything. Something changed, the water came or was released, and it stayed. The two broad mechanisms that planetary scientists point to are not mutually exclusive, which is part of why the question is still open, because the answer is probably some proportion of both, and the proportions are what's being argued. The first, outgassing. As the magma ocean cooled and the molten rock solidified, volatile compounds that had been trapped in the minerals, water, carbon dioxide, sulfur compounds, were released. Exhaled, in a sense, by the cooling planet. The early atmosphere would have thickened with this outgassed material, and as temperatures dropped far enough, water vapour would have condensed, come down as rain onto a surface still hot enough in places to immediately re-evaporate it, and then rained again, and again for thousands of years, until the surface had cooled enough that the water falling on it could stay. The second, delivery. The outer solar system beyond the snow line was full of ice, water ice incorporated into the bodies that formed there, comets and asteroids and the debris of that cold, distant region of the disk. Jupiter's migration, the late heavy bombardment, the general dynamical chaos of the early solar system, all of these sent material from the outer solar system on inward trajectories, and some of that material hit Earth, and some of what hit Earth was ice-rich. The water in those impactors vaporized on contact and then recondensed as the surface cooled, joined whatever was already here. How much came from each source? The best current evidence, from the ratios of hydrogen isotopes in Earth's water compared to the ratios in different classes of comets and asteroids, points toward a significant contribution from asteroids, particularly the carbonaceous chondrite type, whose hydrogen isotope ratios most closely match Earth's oceans. Comets, for a long time the intuitive candidates, turn out to have hydrogen isotope ratios that don't match quite as well. But this is still being refined. New measurements complicate the picture regularly. Set the debate aside for a moment. Set the isotope ratios and the delivery mechanisms and the competing models aside, and think about what happened at the surface, water pooled, on a planet that had spent its first tens of millions of years in a state of continuous violence, accreting, differentiating, being struck by Theia, cooling from a magma ocean, being battered by the ongoing bombardment of the late heavy period, water pooled, found low points in the cooling crust, gathered in them, and sat. Not dramatically, not with any announcement. The first ocean on Earth was not an event. It was an accumulation in the most literal sense of that word. Water arriving or emerging in quantities that exceeded what evaporation could remove, filling the basins that the cooling crust provided, spreading. There is a smell that comes from dry ground when rain finally reaches it. Something earthy, sharp, briefly overwhelming. It has a name, petrichor, and it comes from compounds released by soil bacteria and plant matter. There was no soil bacteria on the early Earth, no plants, but the first rain falling on cooling volcanic rock would have had its own version of that chemical release. The specific volatile compounds in the rock surface responding to sudden moisture. A smell with no one to smell it, rising into an atmosphere of carbon dioxide and nitrogen and water vapour, above a surface of dark basalt and pooling water. Just water. Dark cold at the surface, still geothermally warm below. Sitting under a sky that would have looked nothing like the sky above you now. No oxygen, no ozone. The sun appearing through a thick atmosphere that filtered its light into something dimmer and redder. The moon still enormous overhead, raising tides in the new water that were enormous, genuinely. The word doesn't quite cover it. What the oceans made possible is a list so long it eventually includes everything, which makes it almost meaningless to recite. Liquid water is the medium in which Earth's chemistry happens, not a container for life, participant in it, a solvent, a reactant, a thermal buffer, a medium for the transport of nutrients and the concentration of organic compounds. The origin of life is its own vast, uncertain territory, and this chapter isn't going there. But the precondition for that territory, the liquid water, present and persistent on the surface, was itself not guaranteed, and its arrival was not trivial. A planet slightly closer to the Sun would have had a different water story. The runaway greenhouse effect, where increasing temperature increases evaporation, which increases the water vapor greenhouse effect, which increases temperature further, until the oceans boil and the water is lost to space, is not hypothetical. It is most likely what happened to Venus. Venus probably had liquid water once, early in its history, before the sun brightened enough to push it past the tipping point. The water is gone now, broken apart by ultraviolet radiation in the upper atmosphere, the hydrogen lost to space, the oxygen reacting with surface rock. Earth sits far enough from that tipping point that the warming sun has not pushed it past. Yet. The margin is real but not infinite, and the sun is still brightening, and this chapter is not the place for that part of the story. But the distance between Earth's ocean and Venus's dry, crushing heat is smaller than it's comfortable to think about. The early ocean covered most of Earth's surface. The continents as we know them didn't exist. The crust was thin, actively volcanic, being churned by a mantle still hotter and more vigorous than today's. What land existed was low and frequently submerged. The boundary between rock and water, not a dramatic coastline, but something more gradual, more provisional. The ocean was not deep everywhere, not shallow everywhere, just present, spreading across the surface of a world still figuring out what its surface would be. And it was dark. The thick early atmosphere scattered and dimmed the sunlight differently than our atmosphere does now. The ocean surface under that sky would have had a quality of, not twilight exactly, but permanent overcast. A diffuse grey light reflecting off dark water, with the enormous moon moving through clouds above it, no sound you'd recognise. No wind shaped by continental coastlines, because the coastlines were barely there. Just water moving under gravity and tide in the dark. This is where the chapter ends up, every time I follow it honestly. Not with chemistry or delivery mechanisms or isotope ratios, which are all real and all important. With the image of standing water on a cooling rock 4 billion years ago, under a dim sky and an oversized moon, not knowing, because water doesn't know anything, what it was the beginning of. It was just there, and it stayed. We already covered the impact. Theia, Mars-sized, 40 to 60 million years into Earth's history, the mixed debris ring, the rapid coalescence. You have that. This chapter isn't going back to it. What this chapter is about is something shorter and harder to say. The moon is made of catastrophe. That's the plain version. The material that forms it, the silicate mantle rock, the mixed outer layers of two planets, was, before the impact, part of something else. Part of Earth's early mantle, part of Theia's. The collision didn't add a moon to Earth. It rearranged existing material into a new configuration, a new body, orbiting at a distance that has been slowly increasing ever since. Nothing about that origin is gentle. And yet the moon, as an object in the sky, is about as gentle a presence as the solar system offers. Soft light, reliable cycle, the same face always turned toward us, tidally locked, its rotation period exactly matching its orbital period, a gravitational consequence that took millions of years to settle into place. The moon shows us one side and has always shown us one side, for as long as anything on Earth has been capable of noticing, the far side exists. Obviously, we've photographed it extensively, but it has never been seen from Earth's surface by unaided eyes, not once in 4.5 billion years. And there's something in that fact I find not troubling exactly, but worth sitting with. The thing we know best, the night sky's most familiar presence, has a half we've never directly seen. It keeps that half turned away, not deliberately, just physically, the retreating part, 3 to 4 centimeters per year. The moon moves that far from Earth, annually. And this has been happening since the moon formed, though the rate has varied. Faster sometimes, slower others, depending on ocean geometry and continental arrangement and the efficiency of tidal energy transfer. The current rate is not the average rate, but the direction has been constant, outward, always outward. Here is the part that I find genuinely strange, and I want to say it simply without building it up. There will come a time, far future, billions of years from now, when the moon is far enough away that it can no longer produce a total solar eclipse. The geometry requires a specific apparent size in the sky, and as the moon recedes, that apparent size shrinks. Right now, by what feels like an almost suspicious coincidence, the moon's apparent diameter as seen from Earth almost exactly matches the sun's apparent diameter. Total solar eclipses are only possible because of this. The moon covers the sun almost perfectly, not because of any design, just because of where the moon happens to be in its long outward journey at this particular moment in Earth's history. We live in the eclipse window. It will close, slowly, over hundreds of millions of years, but it will close. I don't know what to do with that, so I'm just leaving it there. Moonlight through a window at 3 in the morning has a specific quality that isn't quite like anything else. Not warm, not cold either. It doesn't actually carry temperature. It's just reflected sunlight. And the sensation of coolness people associate with it is mostly a psychological response to nighttime and stillness. But it's present in a way that outdoor light during the day isn't. It finds the edges of things, the corner of a room, the line where the ceiling meets the wall. It's dim enough that you see it rather than see by it. That light took about 1.3 seconds to reach you from the moon's surface. Before that, 8 minutes from the sun to the moon. The light is old by the time it finds your window, not in any meaningful cosmic sense, but old enough, 10 minutes of travel, that the source of it has moved slightly since it left. Everything is moving. The moon away from Earth, Earth around the sun and the sun around the galaxy through the local group. None of it perceptibly on any night to anyone lying still and watching moonlight cross a ceiling. The moon stabilizes Earth's axial tilt, holds it in a narrow range roughly between 22 and 24.5 degrees that keeps the seasons seasonal rather than catastrophic. Without it, the tilt would wander. Models suggest it could reach angles that would make Earth's climate essentially unrecognizable. Whether life could have emerged or persisted under that kind of variability is not a question with a clean answer. So the moon holds something steady that we never feel being held. A stabilizing presence we cannot perceive, working continuously without acknowledgement, formed in violence, retreating slowly, holding steady what would otherwise drift. That's the moon, briefly explained. And now, as promised, left alone, it's up there, or it was earlier, or it will be later, depending on the night and the hour, the same object that coalesced from vaporized rock 4.5 billion years ago, the same face turned toward you that was turned toward the first things on Earth that had eyes, moving away at 3 to 4 centimeters per year, showing you exactly what it has always shown. The near side, the familiar craters, the flat dark plains the early astronomers called seas, because they thought they might be. They aren't seas. There is no water on the moon's surface. But once, very briefly, 4 billion years ago, the material that became the moon was water-rich, mixed into the debris ring from Thayer's outer layers, from Earth's early crust. Most of that water was lost to space during the violent condensation process. Some small amount may remain in permanently shadowed craters near the poles, frozen, ancient. Ice in the dark on the moon, that was once part of Earth, left alone now. The solar system settled. That's the whole chapter in some sense. The rest is just trying to feel what those 3 words actually mean, which turns out to be surprisingly difficult. After the moon-forming impact, after the magma ocean cooled, after the oceans pooled and the early crust thickened, and the last of the heavy bombardment gradually, not suddenly, there was no sudden, just a statistical slowing over hundreds of millions of years, tapered off. After all of that, the solar system reached something like its current configuration. 8 planets on roughly circular orbits, the asteroid belt sitting between Mars and Jupiter, depleted and stirred and settled into the orbital structure it would keep. The outer planets parked at their respective distances, their gravitational relationships worked out, their resonances established. And then it just kept going. That's what's hard to convey, not what happened next, what didn't. The structure of the solar system from roughly 3.5 to 4 billion years ago until now has not changed in any fundamental way. The planets are where they were. The sun has burned steadily, brightening very gradually, about 30% brighter now than at ignition, a change so slow it is invisible on any timescale a human civilization could perceive. The asteroid belt has lost material to occasional impacts and gravitational ejections, but its basic character is the same. The Kuiper belt exists at the same distance. Neptune is where Neptune has been. Nothing moved, nothing reorganized. The solar system found a configuration that worked and held it for 4 billion years. I want to try something, and I want to be honest that it probably won't work. 4 billion years. The number is so large that the human brain, my brain, your brain, any brain shaped by evolution to track seasons and lifetimes, and maybe the occasional century, simply cannot process it as a duration. We say the number, we nod, we move on. The number doesn't land, it can't. There is no cognitive architecture for it. The oldest thing a human being is likely to personally encounter, a sequoia, an ancient stone building, a geological formation with an age you can read on a sign, might be a few thousand years old, maybe 10,000 at the outside. Even that already exceeds intuition. 10,000 years ago, humans were just beginning to domesticate wheat. The pyramids weren't built yet. Nothing you'd recognize as a city existed anywhere on Earth. Now multiply that by 400,000, that's 4 billion years, and the solar system just sat there. Planets orbiting, the sun burning, nothing in the large-scale structure changing enough to notice if you were watching from outside at any normal speed on any human timescale. I cannot feel that duration. I can write the sentence. That's not the same thing. There's a specific quality to deep boredom, not the shallow kind and not the kind that comes from waiting 20 minutes for something, but the deeper kind. The kind that sets in after hours of genuine inactivity, where time starts to feel less like a river and more like a room you can't leave. It gets heavy. The air gets heavy. The clock in the corner, if there is one, starts to feel less like an instrument and more like a fact of the room, just part of the furniture ticking because that's what it does. 4 billion years is that feeling, except the room is the solar system and the clock is the sun, and the furniture is 8 planets on circular orbits, and nobody is sitting in the room feeling bored because there is nobody. And the duration makes any human experience of waiting feel like a held breath. The metaphor doesn't reach. I know it doesn't reach. I'm leaving it anyway. On Earth, during this interval, things were happening. Life emerged, probably within the first billion years, possibly much earlier, in the hot chemistry of early oceans or hydrothermal vents or somewhere else still being argued about. Life then spent the next 2.5 billion years as single-celled organisms, doing almost nothing visible, slowly oxygenating the atmosphere in a process so gradual it registers as catastrophic only in retrospect. Complex multicellular life appeared somewhere around 600 million years ago. Animals with hard bodies, things that leave fossils, showed up around 540 million years ago, in an event called the Cambrian explosion, which is an explosion only by geological standards, having taken place over tens of millions of years. And then the remaining 540 million years produced everything else. Every species that ever left a fossil, every extinction event, every ocean, every continent in its various positions, every ice age and warm period and mass die-off, all of it compressed into the last 12% of Earth's current age. The solar system, during all of this, just kept doing what it was doing. Orbits, gravity, the sun burning. This is the part that I find not humbling exactly, because humbling implies I had an inflated sense of scale to begin with. I find it clarifying in an uncomfortable way. The solar system does not care about the things that happen on its surfaces. It doesn't register them. 5 mass extinctions on Earth, the most severe of which killed something like 96% of all marine species and perhaps 70% of all terrestrial vertebrates, and the solar system's structure didn't twitch. The Sun continued its fusion. Jupiter stayed where Jupiter was. The orbital mechanics processed onward, indifferent and precise. This is not a tragedy, it's not anything. It's just the difference in scale between what we experience as significant and what registers at the level of solar system dynamics. The scales don't intersect. They run parallel, enormous and intimate, and they don't touch. The asteroid belt during this long interval has been slowly losing mass. Collisions between belt objects produce debris, and that debris, depending on its size and the specific orbital mechanics acting on it, either drifts inward toward the Sun or gets ejected outward. Over 4 billion years of this slow grinding, the belt has lost a significant fraction of what it contained, even after Jupiter's migration depleted it. What's left is roughly 4% of 1% of Earth's mass, as I mentioned before, spread across a volume of space enormous enough that if you were travelling through the belt, you would almost certainly never see one asteroid from another. The belt doesn't look like it does in films. It's not a crowded debris field. It's mostly empty space with objects separated by hundreds of thousands of kilometres. The drama happened early. What remains is the residue of that drama, sitting in its orbits, slowly losing members. Somewhere in the outer solar system, during this same long interval, the Oort cloud has been doing something so slow it barely qualifies as doing. A vast spherical shell of icy objects extending perhaps a quarter of the way to the nearest star, disturbed occasionally by the gravitational influence of passing stars or the galactic tide, releasing the odd comet into the inner solar system on an orbital journey of millions of years. Some of those comets reached Earth. Some of them hit the ground. Some of the water in your body may have arrived that way, not recently, but over the long accumulation of impacts across geological time. The Oort cloud is still there, still being gently perturbed, still occasionally releasing something inward. 4.5 billion years. The solar system formed, settled, and then, from the perspective of its own large-scale structure, waited. Not for anything. Waiting implies expectation, and the solar system has none. It simply persisted in its configuration. Planets orbiting, sun burning, the architecture holding, while on one small rocky world in one ordinary orbit. Chemistry did something improbable, and then something more improbable, and then something more improbable still, and eventually produced the specific arrangement of matter lying here, following this thought, in a room somewhere on the surface of the third planet. The solar system didn't notice. The solar system doesn't notice anything, just keeps going. The same orbits, the same sun, the same patient, indifferent architecture, while on one of its surfaces briefly things happen that feel significant, and the sun burns, and the planets orbit, and the clock ticks in the corner of the room. The sun will outlive everything you have ever worried about, every deadline, every argument, every civilizational concern that feels pressing in whatever year you happen to be lying here reading this. The sun will still be burning, when all of it is so thoroughly resolved by time that the resolution doesn't even qualify as history anymore. It will burn for another 5 billion years, give or take, which is, by any measure that touches human life, essentially forever. And yet, the sun is temporary. Both of those things are true, and the chapter is about holding them at the same time, which is harder than it sounds. Here is the Sun's situation, stated plainly. It is a star of middling mass, not the largest, not the smallest, comfortably average in the way that makes astrophysicists use words like solar type as if it's a category worth naming. It formed, as we've covered, roughly 4.5 billion years ago from a collapsing molecular cloud, and it's been fusing hydrogen into helium in its core ever since. The fusion produces energy. The energy produces outward pressure. The outward pressure balances gravity. The Sun holds its shape, maintains its temperature, and delivers approximately the same quantity of light to the same 8 planets day after day, with a reliability so complete that every calendar ever made by every civilization has depended on it without needing to think about it. The Sun has been doing this for 4.5 billion years and has enough hydrogen to continue for approximately 5 billion more. To put that in perspective, the Sun has been burning steadily for longer than complex animals have existed on Earth, and it still has more than enough fuel left to do the whole thing again. The Sun is, by any reasonable assessment, extremely good at its job, but the hydrogen is not infinite, and the accounting matters. Every second, the Sun converts roughly 600 million tons of hydrogen into helium, 600 million tons per second, and the mass equivalent of about 4 million tons of that, the difference between the input hydrogen mass and the output helium mass, is released as energy, per Einstein's relationship between mass and energy. This has been happening for 4.5 billion years. The Sun has lost a meaningful fraction of its original hydrogen. Not most of it. The Sun is large enough that even this profligate rate of consumption leaves plenty, but a fraction. The core, specifically, is where the depletion matters. The outer layers of the Sun are not hot or dense enough for fusion, only the core sustains it. And in the core, the proportion of hydrogen is lower than it was at the Sun's formation, and the proportion of helium, the ash of fusion, inert and accumulating, is higher. This is fine currently. The remaining hydrogen is still sufficient, the core conditions are still right, the balance of fusion pressure against gravity still holds. The Sun has not noticed any problem, to the extent that the Sun notices anything. Which it doesn't. I just want to be clear that the Sun is not sitting there anxiously watching its hydrogen levels the way you check a phone battery. It's just physics. But the helium is accumulating, and accumulating helium over billions of years changes the conditions of the core in ways that have consequences. As helium builds up in the core, it acts as a kind of ballast. Helium nuclei are heavier than hydrogen nuclei, and a core increasingly dominated by helium requires higher temperatures and pressures to maintain the fusion rate needed to balance gravity. The Sun compensates automatically through the physics of stellar equilibrium by contracting the core slightly, which raises the temperature, which sustains the fusion, which maintains the pressure balance. This compensation works. It has been working for 4.5 billion years. But it has a side effect. As the core temperature increases, the outer layers of the Sun expand slightly, and the total luminosity, the total energy output, increases. The Sun today is roughly 30% brighter than it was when the solar system formed, and it will continue brightening slowly and continuously for the rest of its hydrogen-burning lifetime. 30% brighter, over 4.5 billion years. A rate of change so slow that no instrument in human history could have detected it happening in real time, and yet cumulative enough to have genuine consequences for planetary climates over geological time. The early Earth under a younger and dimmer Sun should have been frozen, the so-called faint young sun paradox, which is resolved by higher concentrations of greenhouse gases in the early atmosphere. though the details are still being worked out. The future Earth, under a brighter and brighter sun, faces the opposite problem. That's the next chapter's territory. What I want to stay with here is the biographical framing. The sun has a biography. This is not a metaphor. It's a description of a physical object with a beginning, a middle, and an end. Each phase characterized by different internal conditions and different external appearances. The sun is currently in what stellar physicists call the main sequence, the long, stable hydrogen-burning phase that occupies the majority of a star's active life. Main sequence stars are, by the standards of stellar evolution, boring. They sit in one place on the diagram, fusing hydrogen, maintaining equilibrium, not doing anything dramatic. The sun has been boring for 4.5 billion years. It will be boring for 5 billion more, and then it will become very suddenly, by stellar timescales, extremely interesting. Nobody who would appreciate this is likely to still be around for it. The biography of a star like the sun has a shape. Long, stable middle, preceded by a brief and turbulent formation phase, followed by a relatively rapid, in stellar terms, transition through giant phases and ultimately to a white dwarf. The main sequence is most of the life. The end phase is a small fraction of the total, but the end phase is where most of the physics that matters for the solar system's fate occurs, which is why it gets its own chapters. There's a specific quality to late summer afternoon light, not the bright overhead light of midday, but the slightly lower, slightly warmer light of 4 or 5 o'clock in August, when the angle has changed just enough to feel different, without being obviously dimmer. That light is harder to describe than to recognize. It has a particular quality of duration in it, a feeling of the day having been going on for a while. The sun's light, at this point in its biography, has that quality. Not visibly. You cannot look at the sun and see that it has been burning for 4.5 billion years, and I would recommend not trying to look at it directly under any circumstances. But the light reaching Earth right now is the light of a middle-aged star, slightly brighter than it was in the beginning, carrying in its spectrum the physical record of 4.5 billion years of continuous fusion. The light is old in a way that has nothing to do with how it looks. It left the sun's surface 8 minutes ago, but the story it carries is much longer than that. The hydrogen in the core will last another 5 billion years. That number keeps coming up, and I want to resist the temptation to make it feel long or short. It's neither really, in any framework that makes sense. It's just the remaining duration of the current phase. After it, the core conditions change, the equilibrium breaks, the sun begins to do something different. What it does next is not a catastrophe exactly. It's a transition, a physical consequence of the accounting catching up, the helium ash accumulating past the point where the hydrogen-burning equilibrium can compensate, the core contracting and heating past the threshold where the outer layers can stay where they are, the sun beginning to expand in the slow, enormous way that stars of its mass expand when the main sequence ends. This process will take hundreds of millions of years to complete. It will not happen quickly. The sun will not one day abruptly become something different. It will drift, slowly. The way afternoon drifts into evening, no single moment you can point to, just a quality of the light that keeps changing day after day until you look up and notice that something is different. The sun is not permanent. It's just very, very patient about it. There is no moment when it starts. That's the first thing to understand, and probably the hardest, because the human mind is very good at finding moments, at locating the point where one thing became another, the frame where the before ended and the after began. The sun's expansion into a red giant does not have that frame. It has a process, spread across hundreds of millions of years, in which the conditions of the inner solar system shift so gradually that any observer moving through it in real time would perceive nothing changing at all. And yet the cumulative shift is total, complete. The inner solar system that exists now and the inner solar system that will exist when the Sun reaches the end of its main sequence are not the same place. The physics between them is continuous. The difference between them is everything. Start with the light. The Sun is already brighter than it was at formation, 30% brighter as we have covered, and it will continue brightening as the helium accumulates in the core and the fusion zone adjusts. This brightening is not linear and not dramatic at any given moment, but it is relentless, in the way that compound interest is relentless. Nothing noticeable in any single interval, everything changed across enough intervals. Over the next billion years, the Sun's luminosity will increase by roughly 10%. That sounds modest. It isn't. A 10% increase in solar luminosity, sustained over geological time, is enough to tip planetary climate systems past thresholds they have been sitting near, some of them uncomfortably near for their entire histories. The difference between a planet with liquid water on its surface and a planet without is often not a large difference in energy input. It's a threshold. A tipping point past which feedback mechanisms that previously stabilized the climate begin to work in the opposite direction. Warming leading to evaporation, leading to more greenhouse effect, leading to more warming. The familiar physics of runaway, which is not a metaphor but a description of a real dynamical state that real planets reach. Venus reached it, probably. The current evidence suggests Venus had liquid water early in its history, a cooler, younger sun, a Venus that sat inside the habitable zone, oceans of a sort maybe. And then the sun brightened, incrementally, over hundreds of millions of years, and Venus crossed a threshold from which there was no return. The oceans evaporated, the water vapour thickened the atmosphere. The greenhouse effect intensified. The remaining water was eventually broken apart by ultraviolet radiation in the upper atmosphere. The hydrogen lost to space, the oxygen absorbed by surface rock. What remained was the Venus we can measure now. Surface temperature of 465 degrees Celsius, atmospheric pressure 90 times Earth's, clouds of sulfuric acid, no water anywhere. Venus is not a warning about the future. It's a record of the past, of what the sun's brightening does to a planet that sits slightly too close given enough time. The warning was always there. It arrived too early by several billion years for anything on Earth to read it. Earth's situation is more gradual and more uncertain, and I find it, and I also want to say this plainly without making it sound more dramatic than the physics warrants, genuinely hard to sit with. The Earth has managed, across 4 billion years of increasing solar luminosity, to maintain conditions suitable for liquid water on its surface through a set of feedback mechanisms that are elegant in the specific sense of being physically real and not designed. The carbonate-silicate cycle primarily, a geological thermostat in which higher temperatures increase the rate of silicate weathering, which draws down atmospheric carbon dioxide, which reduces the greenhouse effect, which cools the planet. And when temperatures drop, the weathering slows, carbon dioxide accumulates from volcanic outgassing. The greenhouse effect increases, the planet warms. Back and forth, over millions of years, keeping Earth within a range that liquid water tolerates. This thermostat has worked for 4 billion years. It will not work forever. As the sun brightens further over the next 1 to 2 billion years, the estimates vary and the models disagree on the precise timeline. The thermostat will run out of room. The carbon dioxide concentration in the atmosphere will be drawn down to levels too low to support complex plant life, as the weathering rate required to compensate for the increased solar input strips the greenhouse gas faster than volcanism can replenish it. The plants die, the oxygen cycle changes. The food chains built on photosynthesis, which is to say essentially all of them, lose their foundation. This is not an impact event, not a supervolcano, not a gamma-ray burst or a nearby supernova, or any of the acute catastrophes that populate the extinction literature. It is just the sun, brightening the way it has always been brightening, crossing a threshold that the Earth's regulatory systems cannot compensate for, not because anything went wrong, because the sun kept doing what it does, and the Earth sat where it sits, and the gap between them eventually became the wrong size. The oceans will not immediately boil. The timeline from the first serious climate disruption to the actual loss of surface water is itself hundreds of millions of years long, full of intermediate states that are genuinely difficult to predict. But the direction is set. The sun is moving in one direction, and the Earth's capacity to adapt has limits, and the limits will eventually be reached. 1 to 2 billion years from now, by most estimates, give or take. The uncertainty is real, and the models span a meaningful range, and I am not going to pretend to more confidence than the science has. Mercury during all of this. Physicist is largely irrelevant to the story of expanding heat. It has almost no atmosphere to lose, almost no volatile material on its surface, and its proximity to the sun means it has been subjected to conditions that would count as extreme by any other planet's standards for its entire history. Mercury is already, in a sense, what the inner planets will eventually become: a bare, airless, heavily cratered rock, indifferent to the sun's output because there is nothing left on its surface that the sun can take. The transition from now to the sun's red giant phase will not change Mercury's fundamental character. It will just get hotter. The specific temperature Mercury will reach when the sun expands fully is not a number that carries much meaning in ordinary language. Enough. More than enough. Mercury will not survive the red giant phase intact, most models suggest. Though the exact fate depends on orbital evolution over billions of years, that is genuinely hard to calculate precisely. Mars is, and this is the part of the story that carries an unexpected quality, something almost wistful. Mars is a different case. Mars currently sits outside the habitable zone. Too cold, too thin in atmosphere, too small to have retained the geological activity that might have sustained its early warmer period. But as the sun brightens, the habitable zone moves outward. The band of orbital distances within which a planet could support liquid water on its surface shifts outward with the sun's increasing luminosity, slowly, over hundreds of millions of years, and Mars is in the direction of outward. There is a period distant, genuinely uncertain in its details, but physically plausible, during which Mars might sit inside an expanded habitable zone, a warmer Mars, not Earth-like, not dramatically transformed, but warmer. Whether that warmth is sufficient to do anything meaningful, given that Mars has lost most of its atmosphere and most of its internal heat and most of the geological mechanisms that would allow it to respond to a changed energy environment, this is where the models become genuinely speculative, and I want to be honest that the honest answer is, we don't know. Mars might have a moment, or something that by generous interpretation resembles one, or it might simply be a cold, thin-aired rock receiving slightly more sunlight than it does today, insufficient to change anything that matters. The physics allows for both outcomes, and the difference between them depends on factors we cannot currently calculate with confidence. The outer solar system during this long warming of the inner planets is doing something worth mentioning, though its full significance belongs to a later chapter. The icy moons. Europa, Enceladus, Titan, bodies that currently sit in conditions of permanent cold, their water locked under ice shells or frozen into surface chemistry. Their potential for liquid water dependent on internal heat sources rather than solar input. As the sun brightens and the habitable zone moves outward, the outer solar system receives more energy than it does today. Not enough initially to dramatically change the ice-covered moons, but the direction of change is toward them. Over the long timescale of the sun's expansion, the hundreds of millions of years between now and the red giant phase, the energy reaching Jupiter's system and Saturn's system will increase. How much this matters for the ice-covered moons depends on details of their ice shell thickness, their internal heat production, their orbital dynamics. The answers vary by moon and by model, but the outer solar system is not static during this period. It is slowly, incrementally, receiving more light from a sun that is slowly, incrementally producing more of it. The habitable zone moves outward. The inner solar system slowly empties of the conditions that made it habitable. The outer solar system slowly warms towards something it has never been. There is a room-warming quality to all of this that I keep returning to. Not the sudden, uncomfortable heat of a summer afternoon, but the slow kind. The kind where you've been inside all day, and at some point you notice that the air has a different weight to it, slightly stale, slightly warm, and you realize the room has been changing for hours without any moment you could have identified as the change beginning. The inner solar system is that room. The sun is what has been warming it continuously for 4.5 billion years. The change has been too slow to perceive on any human timescale, across any span of human civilization, across any span of time that human history covers. But it has been happening. The room has been warming, and at some point, not soon, not in any time frame that touches anything living today, but at some point that the physics makes inevitable, it will become too warm, not loudly, not all at once, the way dusk changes a room, the light shifting so gradually that there is no moment you could name when the day became the evening, just incrementally, inevitably, the sun growing and the inner solar system receiving it, and the conditions that made this place what it is slowly, quietly becoming something else. The sun will not explode. It's worth saying at the start because the word red giant carries for some people an implication of violence, of something rupturing, detonating, the solar system ending in a flash. That's not what happens. What happens is slower, and in some ways stranger, and in the long run more total than any explosion could be. The sun will swell when the hydrogen in the core finally depletes, past the point where the equilibrium can hold, when the helium ash has accumulated enough that the core contracts further under gravity, heats past the temperature where hydrogen in the shell surrounding the core ignites, and the energy output increases past the point where the outer layers can stay where they are. The sun will begin to expand. The outer layers, pushed by the increased energy flux from below, will move outward. Slowly, over hundreds of millions of years, the sun's radius will grow from its current size, large enough to contain roughly 1 million Earths by volume, to something roughly 100 to 200 times larger. The surface temperature will actually drop during this expansion. More surface area radiating the energy means each square meter of surface is cooler than before, even as the total luminosity increases enormously. The colour shifts, from the yellow-white of the current sun to something redder, deeper, the specific colour of a star whose surface has cooled to roughly 3,000 to 4,000 Kelvin. Red, hence the name. The light reaching the solar system will change quality entirely. Not dimmer, the total energy output will be far higher than today's sun, but different in its color distribution, weighted toward longer wavelengths, the kind of light that would make familiar objects look wrong, surfaces appearing darker and redder than they do under current sunlight, shadows having a different quality. The whole visual register of the solar system shifted into something that shares almost nothing with the afternoon light falling through your window now. Mercury will be gone before the sun reaches full red giant size. The orbital dynamics of Mercury are already slightly precarious. It has the most eccentric orbit of the inner planets, and over very long time scales the gravitational perturbations from the other planets create a small but real probability of orbital instability. By the time the Sun is expanding significantly, Mercury's fate is almost certainly sealed regardless of orbital mechanics, because the expanding solar atmosphere will begin to exert drag on Mercury's orbit well before the Sun's radius reaches Mercury's current orbital distance. The orbit decays, Mercury spirals inward. It is absorbed. This is not a collision in any meaningful sense. Mercury will not strike the Sun's surface. The red giant Sun doesn't really have a surface the way a main sequence star does. It will pass into an atmosphere that becomes progressively denser as it moves inward, decelerating, losing orbital energy to drag, falling. The material that was Mercury will be dispersed into the outer layers of the Sun. That process takes, I want to be honest that the exact timeline is model dependent and the models have real uncertainty at this level of detail, perhaps millions of years from the point when drag becomes significant, which is, by the standards of what we've been discussing, fairly quick. Mercury, done. Venus presents a similar outcome, arrived at slightly later. Venus sits farther from the Sun than Mercury, and its fate during the red giant phase has been modelled extensively, and the models broadly agree. Venus will not survive. The same drag mechanism, the same orbital decay, the same dissolution into the expanding solar atmosphere. Venus is the second planet, and it will be, in the end, the second to go. What's strange about Venus's fate, and I'm not sure strange is the right word, but it's the one I keep reaching for, is that Venus was probably the first inner planet to lose its habitability billions of years ago when the young sun's gradual brightening pushed it past the runaway greenhouse threshold, and it will be among the first to be consumed by the dying sun. Venus has been, from the perspective of biological potential, unfortunate at both ends of the story. Too close at the beginning, too close at the end. The middle, admittedly, was not great either. Earth. The models genuinely disagree about Earth's fate during the red giant phase, and I want to stay with that disagreement rather than paper over it, because it matters and the uncertainty is real. The question is whether the Sun's expansion will engulf Earth's current orbital position, and the answer depends on two things that are hard to calculate simultaneously: exactly how large the Sun grows, and exactly where Earth's orbit is when that happens. The second part, Earth's orbit, is not fixed. As the Sun loses mass during the red giant phase, which it does through an intensified stellar wind that will shed a significant fraction of its total mass over the red giant lifetime, the gravitational hold on the planets weakens. Weaker gravity means wider orbits. Earth will drift outward as the Sun sheds mass, which gives it a fighting chance of staying ahead of the expanding solar radius. Whether it stays ahead is what the models disagree about. Some models suggest Earth migrates outward fast enough to avoid engulfment, surviving the red giant phase as a scorched, airless, waterless rock, but surviving in the sense of remaining a discrete object on a stable orbit. Other models, accounting for tidal interactions between the expanding Sun and Earth's orbit, the same basic physics that is causing the Moon to drift away from Earth, now working between the Sun and Earth, suggest that these tidal forces will actually cause Earth's orbit to decay rather than expand, pulling Earth inward rather than letting it drift out? The honest answer is, we don't know. Earth will either be engulfed or it won't, and the physics that determines which outcome is real and is being actively studied, and the current state of that study is that the outcome is genuinely uncertain. I find that uncertainty, and I want to be careful here about performing a feeling I don't quite have, or having a feeling I shouldn't quite have, I find it appropriate somehow that the fate of the planet you are lying on right now in 5 billion years is not settled, that the universe hasn't decided yet, in the sense that the physical processes that will decide it are still in motion, and their outcome is not written anywhere we can read. What is certain? Whether or not Earth is engulfed, it will not be habitable. The oceans will have been gone for billions of years by the time the red giant phase arrives. The atmosphere, whatever remains of it, will be stripped or baked into irrelevance long before the sun's radius reaches anywhere near Earth's orbit. The surface will be bare rock at temperatures that need no further description. The Earth in the red giant era is not Earth in any sense that matters. It is a rock at a particular orbital distance from an expanding star made of materials that were once a planet, tracing the orbit of something that no longer exists. Mars, sitting farther out, survives the red giant phase. The models are fairly consistent on this. Mars's orbit, widening as the Sun loses mass, stays clear of the expanding solar radius. Mars emerges from the red giant era as a hot, irradiated rock with even less atmosphere than it has today, its surface scoured by the intense ultraviolet and particle radiation of the active red giant Sun, its interior long since cooled and geologically dead. But Mars persists, as an object, as a discrete body on a stable orbit, and in the period during the red giant phase, before the Sun's radius has expanded to its maximum, but after its luminosity has increased enormously. During this period, Mars receives significantly more energy than it does today. Whether this matters for Mars, given the state of Mars's atmosphere and geology by that point, is unclear. Probably not. Probably Mars in the red giant era is simply a hot Mars, receiving more light, not doing anything different with it. Probably. The outer solar system is where the red giant phase produces something that feels, if you approach it without preconceptions about where interesting things should happen, genuinely unexpected. Europa, Enceladus, Titan, the icy moons of Jupiter and Saturn, currently sitting in conditions of deep cold, their surfaces frozen, their potential liquid water maintained only by internal heat from tidal flexing and radioactive decay. As the Sun expands and its luminosity increases by factors of hundreds, the red giant Sun will be vastly more luminous than the current Sun, though the numbers vary by model. The energy reaching the outer solar system increases dramatically. The ice shells of the Jovian and Saturnian moons will receive more solar energy than they do today. How much more, and whether more is sufficient to change the surface conditions of bodies that are currently kept cold by their enormous distance from the Sun, this is genuinely uncertain, and the models span a wide range. But the direction is clear. The outer solar system warms. The habitable zone, which has been moving outward for billions of years as the Sun brightened on the main sequence, arrives in the outer solar system during the red giant phase. Whether it arrives with enough energy, sustained for long enough, to do anything meaningful at the surfaces of the icy moons, whether Europa's ice shell thins, whether Titan's atmospheric chemistry changes, whether any of these ancient, cold, dark worlds briefly enter conditions that liquid water on their surfaces could tolerate, the physics allows for it, and some models suggest it happens, and the duration of the red giant phase is long enough, roughly 1 billion years, that even slow processes have time to develop. 1 billion years is a long time for something to happen in. The red giant sun, at its maximum, will subtend an angle in the sky of the surviving planets that has no comparison to anything in current human experience. Not the moon at perigee, not the sun at any point in its current life. Something much larger, much redder, occupying a portion of the sky that the current sun by comparison barely touches. And then, after a billion years of that, the outer layers drift away, the helium in the core ignites briefly, the star pulsates, the extended atmosphere, no longer bound by the diminished gravity of the mass-losing sun, expands outward into space as a planetary nebula, a shell of glowing gas, illuminated by the hot white core contracting at its center. The solar system, for a brief period in astronomical terms, will be surrounded by a shell of what was once the sun, and at the center of that shell, shrinking and cooling, something small, dense, the sun's core stripped of its outer layers, roughly the size of Earth, incredibly hot, fusing nothing. A white dwarf, that's the next chapter. The planetary nebula will be beautiful. That feels like a strange thing to say about the end of the sun, and I want to be careful not to reach for beauty as a way of softening something that doesn't need softening. The physics doesn't need emotional management. And the solar system's end is not a tragedy in any register that the physics recognizes, but the nebula will, by any optical measure, be beautiful. A shell of ionized gas expanding outward from what was the sun, illuminated by the ultraviolet radiation of the hot white core at its center, glowing in the specific colors of excited hydrogen and oxygen and nitrogen, reds and blues and greens, the emission spectrum of matter that has been heated past the point of ordinary chemistry and is now simply radiating as it expands and cools and disperses into interstellar space. We have photographs of other stars' planetary nebulae, the Ring Nebula in Lyra, the Helix Nebula in Aquarius, sometimes called the Eye of God, though it isn't one. These are the remnants of stars that went through the same process the sun will go through. Their outer layers shed, their cores exposed and hot at the center of an expanding shell. They are, in photographs, among the most visually striking objects in the sky. The solar system will be inside one of these briefly, a few tens of thousands of years maybe. Then the shell will expand past the outer planets, past the Kuiper belt, past the Oort cloud, and disperse into the interstellar medium, thinning until it is indistinguishable from the general background of the galaxy. And what remains is the white dwarf. A white dwarf is not a star in the sense that the sun is currently a star. It is fusing nothing. There is no energy source at its center, no ongoing reaction sustaining an equilibrium against gravity. What holds it up, what prevents it from collapsing further under its own gravity, is electron degeneracy pressure, a quantum mechanical effect that has nothing to do with heat or fusion, and everything to do with the fact that electrons, as fermions, cannot occupy the same quantum state. The white dwarf is supported by the refusal of its electrons to be compressed any further. This support is permanent, in a meaningful sense. A white dwarf does not collapse, it cools. The white dwarf that will be the sun's remnant will have a mass of roughly half the sun's current mass, the rest having been lost during the red giant phase, compressed into a volume roughly the size of Earth. The density that implies is the kind of number that language genuinely cannot carry. A teaspoon of white dwarf material would weigh several tons. The surface temperature, initially, will be in the hundreds of thousands of Kelvin, hotter than the current sun's surface by an enormous margin, despite producing far less total energy, because the radiating surface is so much smaller. And then it cools, slowly, over billions of years, over timescales longer than the current age of the universe, The white dwarf radiates its stored thermal energy into space, dimming, reddening, eventually becoming something theoretical astrophysicists call a black dwarf. A cold, dark, inert mass of electron-degenerate carbon and oxygen, invisible, sitting in the darkness where the sun used to be. If this is the kind of slow, careful science that stays with you, there are extended notes and reflections on this chapter available on Patreon. The link is in the description. No black dwarf has ever been observed. The universe is not old enough for any white dwarf to have cooled to that point yet. The oldest white dwarfs in the galaxy are still faintly warm, still faintly glowing. The black dwarf is a theoretical object, a prediction, something the physics requires but the current age of the universe has not yet produced even once. The sun will become something that, at the time of its becoming, will not yet have any existing examples. The outer planets, Jupiter, Saturn, Uranus, Neptune, will persist. Their orbits, having expanded outward as the sun shed mass during the red giant phase, will have settled into new configurations at greater distances from the white dwarf than they currently orbit the sun. The gravitational dynamics of this reconfigured system will be different from what they are today. The reduced central mass, the changed orbital distances, the altered resonance relationships between the giant planets will take millions to billions of years to fully resolve into a new stability, if they do. Some models suggest that the outer planets' orbits will eventually be destabilized by the combined gravitational perturbation of passing stars. The sun is not alone in the galaxy, and over billions of years, other stars pass close enough to exert meaningful gravitational influence on very wide orbits. The Oort cloud will be severely disrupted during and after the red giant phase, its loosely bound members scattered by the changed gravity of the mass-losing sun and by subsequent stellar encounters. The outer planets themselves, on timescales of billions of years, may be gradually perturbed into unstable configurations, ejected one by one into interstellar space, leaving the white dwarf, eventually, if enough time passes, entirely alone. This will take an incomprehensibly long time, longer than the sun's entire main sequence lifetime, longer possibly than the current age of the universe multiplied many times over. But the direction is set. Slowly the remaining solar system disperses. The cold that will characterize this system, the white dwarf cooling over billions of years, the outer planets on wide dark orbits, no inner planets, no sun in any recognizable sense, has a specific quality that I find difficult to describe without reaching for words that carry too much weight. It is simply cold, the absence of the heat source that has defined this system for 10 billion years. Not a dramatic cold, not the cold of a storm or a winter or anything with weather in it. The ambient cold of a system where the central heating has gone off and will not come back, where the remaining objects orbit a dimming ember that was once a star, where the light reaching those objects is less than the light reaching the outer planets today, and diminishing, and will continue diminishing for longer than the mind can follow. The room, to return to a metaphor from an earlier chapter, has finally gone cold. Not quickly, not all at once. The way a room goes cold hours after the heating fails, the temperature dropping so gradually that there is no moment you could identify as the moment it became cold, just incrementally less warm, across a span of time that makes the word hours feel inadequate, until the cold is simply the condition of the space unremarkable, total. The solar system will not end. That is perhaps the strangest thing about this story's ending. There is no ending in the clean sense, no moment when it stops. The white dwarf will persist, cooling for longer than the universe has currently existed. The outer planets, if they survive gravitational ejection, will orbit it in the dark for billions of years. The asteroid belt, or what remains of it, will continue its slow grinding attrition. The Kuiper Belt survivors will drift on their distant orbits. Everything just continues. Quieter, darker, colder. The sun gives up its last heat. The planets carry their orbits forward into a dark that has no end assigned to it. And somewhere in the interstellar medium, expanding outward at tens of kilometers per second, the atoms that were once the sun's outer layers, hydrogen, helium, carbon, oxygen, the material of 4.5 billion years of stellar life, are drifting outward into the galaxy, thinning, dispersing, mixing with the general interstellar medium, eventually becoming part of the cloud that will collapse into the next star, the next disk, the next set of planets. The material doesn't end. It continues in a different form, in a different place, in a different configuration. It becomes part of what comes next, whatever that is, still.